Okay, electric fields. Um, the idea of a field was first introduced by the physicist Michael Faraday, and he defined a field as a region of influence. Now, there's lots of different types of fields, gravitational fields, electric fields, magnetic fields, a field of light, anything that has a region of influence. So, for example, a light bulb will have a field of light. The further you are away from that light bulb, the less light you see, the dimmer it gets. You could have a field of heat, like around a candle flame. The closer you are, the warmer it is. And the same thing with electricity and magnetism. Now, probably the field that we have the most experience with is a field of gravity. So, created a little table here where we can compare the two fields. So, a gravitational field is created by a mass, whereas an electric field is created by a charge. Now, what's important is that we can only have one type of mass, so there's only one type of gravitational field. But we can have two different types of electric charge, either a positive charge or a negative charge. So there are going to be two different directions to electric fields. The symbol for gravitational field is a lowercase g, and the symbol for electric field is an uppercase E. Don't get that confused with energy. Energy, remember, always has a subscript, like EP is potential energy, EK is kinetic energy. E by itself is electric field. And the units for a gravitational field, well, it's newtons per kilogram, right? How much force on every kilogram of mass. And electric field will have the same or similar units. How much force, newtons, on each coulomb of charge. So the electric field has units of newtons per coulomb. And that gives us a very easy equation for calculating gravitational field. It's just force divided by mass, right? This is Newton's second law, F equals ma, rearranging for the acceleration or the gravitational field, G equals F divided by m. And instead of using F, we substitute in Newton's universal law and we get G times m over r squared. Same thing for electric fields. We have the electric field is F divided by Q, right? Newtons divided by coulombs, force divided by charge. This time we're going to divide Coulomb's law divided by Q. So one of the Q's cancels and we get KQ over r squared. So this tells us the electric field generated by a charge Q. And if we say how far we are from that charge, we can get the magnitude and direction of the electric field. So how do we determine the direction of a field? Well, for a gravitational field, it's quite easy. I take a mass, this pen, and I see which way the mass moves when I release it in the field. So the direction of the gravitational field here in my apartment is downwards. That's the direction the mass moved. Well, we can find the direction of an electric field in a very similar way. But we're going to take a test object. This time we're going to take a positive charge and we're going to put it in the field and see which way it moves. So the direction of an electric field is always the direction a positive charge moves when released in the field. So electric fields and gravitational fields are vector quantities. It's important that you include the direction. So here's a positive charge, and if we wanted to draw the electric field around this positive charge, I would imagine a positive charge at each point, and I would look at which way would that positive charge move. So if I had another positive charge right here, it would be repelled by this positive charge, and it would move in this direction. Same thing as if it was here, or if it was here, or here, and you get the idea. So these lines show me the direction of the electric field. Okay, they're electric field lines. So the direction obviously is indicated by the arrow, and the relative strength of the electric field, or the magnitude, is given by how close the field lines are. So right here, where they're relatively close together, the electric field is very strong. Over here, where the electric field lines are very far apart, the electric field is weaker. So the closer the electric field lines are, the stronger the field. The further apart they are, the weaker the field. So these are our lines of electric field around a positive charge. If I changed it to a negative charge, obviously the direction of the electric field would be in the opposite direction. Right? So it looks very similar to the positive field, but just the opposite direction. Okay, everything would be attracted towards the negative charge. Things get more complicated when I have two charges. Here's a positive and a negative charge. Obviously, between them, the electric field points in this direction. But it will start to curve as you get further away from that center line, and it'll get more exaggerated and the electric field will look something like this. Obviously, if we continued the lines out further out here, we'd see them starting to bend around. And that's our diagram of the electric field around a positive and a negative charge. Now, you might want to often find the net field at a certain point. So for example, if I chose a point right here, label that P, what is the electric field at this point? So what is the magnitude and direction? Now, we know that the electric field at this point is going to have two components. There will be a component due to this positive charge, which is in this direction, away from the positive, but there will also be a component in this direction towards the negative charge. Okay, so what we have are two electric fields, E1 and E2, and to find the net electric field or the total field, obviously we just add them together, but we need to make sure we add them as vectors. So you're going to add, create basically a vector diagram to find the net electric field. So using our equation for the electric field, find the magnitude for each of these vectors and then add them together to find the total electric field. And we can do that at any point around this vector diagram or around this, this example. Any point up here, any point in between, to the left, to the right, it doesn't matter. All you're going to do is find the magnitude for each electric field and add them together, drawing a vector diagram to find your resultant. Okay, so that's basic electric fields. If you have any questions about electric fields, make sure you come and ask me in class.